Ever since the first radio transmission, engineers and scientists have been trying to pack more and more information into the available spectrum. It became important to know what signals were in the air and what could be done to manage the available space. The Tektronix 492 and 496 spectrum analyzers combine laboratory performance and portability to provide the ideal instrument for the job. I'm Steve Kerman, and in this program you'll see 5 applications of these portable spectrum analyzers: measuring random noise, impulse noise, digital radio measurements, the 496 and random narrow pulses, and measuring TV signals on a communication satellite. Noise is all around us. Noise is on the freeway, at airports. In fact, it's all around our environment. In fact, noise is very much like the weather. Everybody talks about it, but not many people know what to do about it. Well, one of the things you can do about noise is measure it. And there are lots of different instruments to measure noise. There are noise power meters and even the conventional oscilloscope. And because temperature and power supply voltages cause noise values to change, the spectrum analyzer allows you to view the noise spectrum as you make the measurement. Basically, there are 2 types of noise: impulse noise and random noise, and we're going to show you how to measure both of them on this FDI application note. Today we're here at the ground station of the Liberty Cable Television System here in Portland, Oregon, to show you how to make a random noise measurement on a television signal. Let's go inside now and make the measurement. Random noise occurs in nature. It's caused by thermal agitation of electrons, and it can be heard as hiss in an FM receiver. You have to remember when you're making noise measurements that noise bandwidth varies with individual applications. So be sure to normalize the bandwidth for your specific measurement. Techniques for doing this are found in 2 spectrum analyzer noise measurement application notes. This is an off-air television signal. Before we actually make the noise measurement, there are a few things that you ought to remember. First, you may have to amplify the signal so that you can measure the noise. The video signal is a pulse signal, so a fairly wide resolution bandwidth like 300 kilohertz is very appropriate. And don't forget to normalize to the television bandwidth from the analyzer's noise bandwidth and compensate for the instrument characteristics after you've made the measurement. First, we measure the amplitude of the peak video carrier, and this is the video carrier pulse, and we measure the peak amplitude at about -25 dBm. Now, to measure the noise, we'll switch to digital storage and digital averaging, moving the baseline clipper to the top of the screen, and we make the measurement midway between the vision carrier and the color subcarrier, somewhere here where the luminance level and the chrominance level is down in the noise. We measured that at about -70 dBm. Now remember, you have to normalize for your noise bandwidth to make an accurate measurement. Once you've done this, the ratio becomes the signal-to-noise ratio of the video signal. Making measurements of impulse noise is also easy using a spectrum analyzer. Man-made noise like that from an automobile engine is called impulse noise. To measure it, you have to determine the impulse bandwidth by using one of several methods and then normalize to the correct bandwidth, just as we did when we measured random noise. But note that impulse noise is expressed in volts per bandwidth, and because EMI is a broadband measurement, most impulse noise bandwidths are normalized to 1 megahertz. In making this measurement, we're using a 492, and it's being powered by a car battery and an inverter. In this way, we're not dependent on any outside power source like that from an adjacent building. In making the measurement, the noise is peaking between 25 and 45 megahertz. We have a broadband peak, and the noise level is -40 dBm. To convert to dB with respect to a microvolt, we add 107 dB to the measurement and get 67 dB above a microvolt. Now the level has to be normalized to a 1 megahertz bandwidth. Finally, in this measurement, you have to take into consideration the antenna correction factor. This is the new digital radio system installed at Tektronix Beaverton plant. We installed the system to improve communications in the metropolitan area between plants in Wilsonville, Walker Road, and the new Vancouver facility. The noise you hear in the background is from air conditioning units that help keep all of this equipment cool. There are 2 main reasons for installing a digital radio. The first is that digital signals are less susceptible to noise and other interference. The second is that different types of communications, like data, voice, and even television, can be combined in a single bit stream and sent out on the radio. A third reason for installing digital is the economy of converting older conventional analog systems to the newer digital types. Microwave systems are found in many diverse locations, and the need to bring the test equipment to the radio makes the 492 an ideal instrument for this application. While the specs of the 492 are appropriate for this task, a special mod, Mod UB, has been developed for digital radio measurements. Mod UB has a wider preselector, a narrower video filter, and more accurate frequency calibration around 6 and 11 gigahertz, the carrier frequencies of many commercial digital radio transmitters. To protect the front end of the analyzer, make sure you connect it to a TWT power coupler on the radio. Now, before we go on, there are a couple of things you ought to know about the digital radio signal. These signals appear like pulsed random noise on a spectrum analyzer, so all the precautions needed for random noise measurements, such as consideration of noise bandwidth and the use of averaging or digital storage, must be used. The last FDI television application and our printed application note on noise will help you review these techniques. The signal we'll be measuring is an 8-phase shift keyed signal, which looks like a sine X over X display. We can see this classical shape as we look at the output of the radio before the filter. We can smooth the display using digital averaging or the video filter. Now, to meet the maximum power output bandwidth requirements of regulatory agencies like the FCC in the United States, a filter in the radio removes nearly all of the side lobes. The loss due to filtering is usually negligible. I have a mask here that not only defines the FCC required bandwidth of 20 megacycles, but also the point at which the measurement is made. Masks like this are provided with the instructions for a digital radio. We also have a mask that fits on the CRT of the spectrum analyzer. Now, this mask tells you where to make the measurement, but it's different for different carrier frequencies. Radios of 6 gigahertz are measured 50 dB down from peak carrier. 11 gigahertz radios are measured 51 dB down. Now, this radio is a 12 gigahertz radio in the industrial band, and we'll be making our measurement, our occupied bandwidth measurement, at 50 dB down. But 50 dB down from what? Well, it's 50 dB down from peak carrier. You can see this on the screen because we have turned off the modulation. Now, frequently you're not able to do that. Perhaps you'd have a standby transmitter, but there's always a way to determine where the peak amplitude of our display is, and that's done mathematically. We can calculate this using what we know about the height of the main lobe. The signal display peak is computed to be 10 times the log of the ratio of the analyzer noise bandwidth over the signaling bit rate normalized to 4 kilohertz. In this case, we see that the main lobe is 36 dB down. Now we can make the appropriate FCC bandwidth measurement 14 dB below the display peak or 50 dB below peak carrier. The FCC does permit some side lobes to be present in the signal, but they have to be at least 80 dB down. Setting the 492 to 2 megahertz and 2 dB per division, the occupied bandwidth of this radio is approximately 19.5. This compares quite nicely with a spec of 20 megahertz. To get a more accurate frequency reading, we have to attach a counter to the local oscillator output on the 492. We then move the cursor down to the minus 50 dB point on our main lobe, and by moving the cursor from one side of the lobe and noting the reading on the counter to the other side of the lobe, and once again reading the counter, we take the difference of these readings, and since we're on the n equals 3 band of the analyzer, multiply this difference by 3, and we come out with a 19.83 megahertz frequency band. There are many other measurements that can and should be made using the 492 on a digital radio. Other applications like multiple carrier balance and spurious output are covered in this application note, the only application note, incidentally, that covers both the spectrum analyzer and the measurements that can be made on a digital radio system. So, for more information on digital radio measurements, be sure to consult the application note. There are many written spectrum analyzer application notes available from Tektronix. Here's a list relating to the topics covered in this program. You can order them from your local Tektronix sales office. Computers like these, switching power supplies, and even automobile ignitions are some of the man-made sources of stray narrow pulses. Next, we're going to show you how to measure these pulses using the Tektronix 496. Before we get started, you should remember this basic rule. The narrower the pulse, the wider the spectrum, and vice versa. And you can see that in this dual display of a pulse and its spectrum. Impulsive signals are broadband. They constitute a voltage spectral density, which is measured in volts per hertz of impulse bandwidth. We'll approximate the impulse bandwidth using the resolution bandwidth of the 496. If you want to make accurate measurements, you'll have to actually measure the impulse bandwidth. Good references for this measurement are found in the March 1979 issue of Microwaves and this tech application note. The 496 is an excellent instrument for measuring impulsive signals. Spectrum analyzer sensitivity is specified as the average internal noise level, but impulsive signals must be peak detected, so we lose the peak to average dB difference, which is about 10 dB. At 1 megahertz resolution bandwidth, this corresponds to about minus 80 dBm peak signal sensitivity. Here's a spectrum of a narrow pulse signal. Notice that we lose almost all of it as we average this low repetition rate pulse train. If the signal is large, we can set the digital peak-to-average cursor between signal and noise, so the noise is averaged while the pulse signal is unaffected. This isn't possible for small signals. At lower rep rates and narrow pulses, digital storage can't quite catch the pulse peaks. As you can see, the shape and level of the spectrum differs with digital storage on and off. To help the digital storage, turn on the pulse stretcher. In fact, it's a good idea to always use the stretcher. For very low rep rate signals, use max hold. With digital storage, max hold helps you get a clean buildup of the shape of the pulse spectrum. Impulsive signals create dynamic range problems too. Here's a graph of typical 496 dynamic range as a function of signal spectrum width. With 1800 megahertz front-end input bandwidth and 1 megahertz display resolution bandwidth, the input mixer is subjected to over 60 dB more signal level than is displayed. As you see here, given minus 80 dBm sensitivity and about minus 10 dBm mixer overload level, we're left with only about 10 dB of dynamic range. Most interference, though, is around 100 megahertz wide. This would be a 40 dB difference, leaving about 30 dB dynamic range. Excellent. To measure whether you're in trouble on overload, change the mixer drive level and see if the measured level changes. If it doesn't, you're safe. Changing the minimum RF attenuator from 10 dB to 20 dB, the display level doesn't change, so we're okay. Going down to 0 dB minimum attenuation, there's a slight change in signal display level. Some compression right there. Let's increase the signal level. Now when we go to 0 dB attenuation, the signal level changes drastically, showing severe compression. Now let me show you how to measure the actual voltage spectral density. At the observation frequency of 140 megahertz, we have a minus 47 dBm display level using a resolution bandwidth of 1 megahertz. But remember, this is a voltage spectral density. It has to be measured in volts per hertz. So let's go to the linear vertical mode. At 200 microvolts per division, we have 5 divisions, or 1,000 microvolts, giving 1 millivolt per megahertz, or 1 microvolt per kilohertz. At this resolution bandwidth, the impulse bandwidth actually measures 800 kilohertz, so the voltage spectral density is really 1 millivolt per 800 kilohertz, or 1.25 microvolts per kilohertz. The entire display is a classical sine x over x shape extending to about 250 megahertz. Remember, the spectrum of most interference is made up of many different interfering pulses, so that the display you get will not be as clean a spectral display as we got earlier. Another thing to remember is that the 496 is DC coupled, so don't apply DC to the instrument unless you use a DC block. It's possible that you might damage the mixer if you apply DC directly to the instrument. Television broadcasters at local and network stations are using satellite transmissions more than ever for news and entertainment programs. Transponder time is available and affordable, and the technology is so portable that you can transmit or receive virtually anywhere in the world. I'm Steve Kerman, and today we're going to show you how the 492 spectrum analyzer plays a major role at Earth stations such as this one at KATU in Portland, Oregon.
In this application note, we'll cover Earth station site selection, transponder identification and antenna polarization, frequency deviation or spectral occupancy, spectral purity, and frequency deviation and percent modulation of the uplink, all measurements made on the Tektronix 492 spectrum analyzer.
For the broadcaster, the portability of the 492 is important. It can be used here at the transmitter, at the studio, or in initial site selection, detecting any radio interference that might impact the location of the ground station antenna.
Once in place, the antenna is aimed at the satellite of interest. The 492 may then be used for several operational measurements. Transponders on communication satellites operate in either a horizontal or vertical polarization. The antenna horn must be properly oriented to receive or transmit the signal, and the 492 can be used to assure proper orientation. Tune the center frequency of the 492 to about 4.2 gigahertz. At the top of the satellite's transmit band, you can see two small signals. This so-called beacon is always present when a bird is operating, even if no transponder is illuminated. To change the polarization of the antenna, the horn must be rotated by 90 degrees. Since the beacon is transmitted in only one polarity, the 492 is used to detect a peak, or in this case, a null, indicating proper antenna orientation.
I might add that on receive only, the polarization doesn't have to be set nearly as sharp as on transmit, but if I'm off 3 degrees either way on transmit, I'll interfere with a neighboring transponder, and the network people would, whoever's running the satellite, would ask me to leave the air until I corrected the difficulty.
Archie Brush also showed us how frequency deviation, or as satellite engineers call it, spectrum occupancy measurements are made.
Well, 492 is practically the only instrument we can easily make the measurement on at this end. And the way we do it is center the video in this case. Somebody is sending video on this transponder, and depress the maximum hold button, and you'll see what's happening is it's remembering everything that went by it.
What's the allowable deviation per channel?
We can go plus or minus about 18 megahertz. So you can see this fellow isn't really filling out. There's 5, 10, and maybe 13, 5, 10, and he does have a group of information there at about 13 or 14. He's really not filling out his occupancy. Could go to 15 plus about 3, way out there and about there.
The 492 is also helpful for making measurements on the uplink transmitter. Looking at the output of the klystron with a directional coupler in the waveguide, both the visual and dual aural carriers can be seen. This additional signal is telemetry from the studio. It's not too large, but must be monitored, kept at a low level, or filtered out.
To observe and measure spectral purity, set the instrument to 200 kilohertz per division, and as you can see, the trace is quite clean. This noise, 600 kilohertz from the carrier, is assumed to be fan noise.
This same analyzer setup is used to detect any spurious signals or intermod products. In this case, max hold is used so the signal may be observed over an extended period of time. Changing the center frequency to 12 GC lets the operator look for the second harmonic. In this case, there is none.
Finally, frequency deviation and percent modulation may be measured using the 492. Consult the exciter manual for the appropriate modulation signal to apply to the uplink.
The signal is usually a pure sine wave. The 492 is then used as if it were monitoring a conventional FM transmitter. The Bessel nulls on the visual and aural carriers are measured separately.
I would say that if you're in an uplink situation where you're actually transmitting to the satellites and the transponders on that satellite, if you don't have something equivalent to the 492, you're really putting your company and your own personal reputation in jeopardy, because there is no way of knowing what's happening without it.
The small tolerance for transmission errors, plus the fact the world is literally looking over the broadcaster's shoulders, makes the 492 not only a valuable tool, but as Archie said, a security blanket, protecting the broadcaster's reputation and his pocketbook. You've just seen 5 applications of the Tektronix 492 and 496 portable spectrum analyzers. For more information, call your local Tektronix Communications Division sales engineer and let us show you how one of our spectrum analyzers can help you with your application.